Okay, so this is theorem 3.2.7 in your book. Okay, so we're going to start out with our three sequence. Our sequences of real numbers. Such that xn is less than or equal to yn is less than or equal to zn for all n in the naturals. And the limit of xn equals the limit of zn. Then the squeeze theorem tells us that y is convergent. And the limit of xn equals the limit of yn, which equals the limit of zn. Okay. Do you remember the squeeze theorem now? No? Okay. Well, then you were reintroduced to it. Okay. So let's go ahead and prove this. So really, what do we know here? Well, this one held for convergent sequences, right? So we cannot just apply the previous theorem because we do not, as of right now, know that y is convergent. Okay, so I just wanted to make that comment real quick. Okay, so let's let L equal the limit of xn and zn. Okay. And let epsilon be greater than 0. What do we know? Well, we know x and z converge, right? Those are convergent sequences. So there exists x and z, correct.
Couldn't those limits both be like infinity or negative infinity?
So typically well,
They wouldn't be convergent then, would they?
it would not be convergent. But typically we don't think about bounding it between two things at that places, right? Because if both of them are going to infinity, right? That's actually a good point.
But it doesn't say that they're convergent.
So that's actually a really good point. But we're saying that y is convergent, right? So in order for y to be convergent,
But we don't.
we don't. So we should actually put that in here. And so our convergent sequences of real numbers and y. Oh yeah, we definitely should put that in there. Because that does cause a loophole, right? So as you just pointed out in Aaron Bartle, right? Because we do actually need to know that those are convergent in order for this to actually show us y is convergent. So since we're eliminating the case where it is not, right, divergent, we have to assume
Just let them.
are. Good job. Okay, so we're making this, we kind of made that as an assumption, right? But we actually did need that in our statement. So x and z are convergent sequences, okay? So that means the absolute value of xn minus our limit is less than epsilon, and zn minus L is less than epsilon for all n greater or equal to k epsilon. And I'm just going to go ahead and make this k epsilon whatever the biggest guy was out of the two. Okay? Questions? What questions do we have? Are we good with that line now? We're good? Okay. So we know that. So now, well, if I take xn, nope. So because we know this inequality, we know xn minus L is less than or equal to yn minus L, which is less than or equal to zn minus L. And this is just true for all n in the naturals, right? Okay. Just making sure we're looking around the room. So xn minus L. What do we know about it? So we know the absolute value is less than epsilon, right? So it's bigger than what? Negative epsilon. And then Zn minus L, that's going to be less than epsilon. So overall, negative epsilon is less than or equal to Yn minus L, which is less than or equal to positive epsilon.
Do you need to include that equal to? It's like strictly less than.
Oh, it's yes, sorry. Strictly less than, yes. Did I? I apparently want to carry my equal sign. And then that's the same thing as saying what? Yeah, so the limit of yn equals L. I'm just following notation from your book here. Okay, questions, concerns, worries? No concerns? No worries? Okay, we're going to go take it back to calculus today. Told you guys we'd go take it back to calculus. So I'm going to go ahead and let you show 2 examples that you can do on your boards. So show what this converges to, and then what this is converging to.